the streaming. I'm just going to double check to make sure that we got it up and running. Looks like it's running. Yep. Okay. All right. This is the wrong class. I'm gonna switch back to CISP440. All right. So I'm not sure what happened. I think I forgot to announce it that there's an assignment from last week. So you noticed. A few other people did too. So I postponed the due date to Wednesday. And a few people turned in something already, and I basically reset it, allowed those people to turn it in again. So if you have any issues with the assignment, just let me know, and I can always kind of reset the attempts. All right. So with that, we are going to get started with Aleph No. This is our new topic. And it is based on functions. So this is why it is important to kind of make sure that all the material introduced up to this point are all done and cleared away, because I am going to stack concepts up pretty much with every single new module. So are there any questions about the function module? Any questions about what makes a function a function? What is a function? What is injection? What is surjection? And what is bijection? No questions? Any questions about notation? So for all, there exist the set notations, the operators. No questions about those? Okay. All right. So we're going to start with Aleph No, and I'm not sure how many people got a chance to read ahead of me or read ahead of the lecture, because this one can be a little bit tricky. There's a lot of stuff, in this particular module. I was trying to explain the reasoning of how I derived, some of the formulae, and on top of that, we are getting into, the whole concept of Aleph No, which is, the cardinality of the set of natural numbers, which at first does not seem to make sense because it has an infinite number of elements, but at the same time, we can actually establish equivalency or equality of the cardinality of sets that actually have an infinite number of elements. So we'll start with this. And this chapter, this module, is actually also partially why this class is called discrete structure or discrete math. What exactly makes it discrete? What makes it different compared to calculus? Because what you learn in calculus is not discrete. It is, well, don't tell your calculus professor that, not in those words. Okay, you guys are, some of you are getting it. Don't say calculus is indiscrete. Okay, maybe I need to refine that one a little bit. Anyhow, so what we'll do is we are going to look at the cardinality of the set of all integers, the cardinality of the set of all natural numbers, and find out why they are the same and why they're both called Aleph No. So that's what we're going to be talking about today. And the question first is, how is this quality established? In other words, how is this equality established that these two sets have the same cardinality? So I think last week I gave you some, a few things to think about. The first one is one set the subset of the other one? Proper subset, not just subset, but a proper subset. And it turns out that was true. Okay, so what I'll do is I am going to use Joplin to denote a few things. So let me switch to today is 0912, and I need to move this to the other window. I can't grab it. right, there we go. I'm not sure how you guys are taking notes, but it's important to take notes, especially when you have some realization, you're connecting some concepts, but not exactly what I'm saying. Because what I'm saying and what is being displayed on the screen is already captured, using the recording. But your own thoughts, what you make connections on your own, is cannot be recorded because first of all, I cannot read your minds. Okay, so that's number one. And two, each person has a different way of understanding the concepts, so only you can write down your own understanding of the concepts. So the first question is, okay, so I'm going to type it up. So for the first question is math BB is the set of all, okay, I need to double check that. Is the set of all natural numbers a proper subset of the set of all integers? And it doesn't like that. Math BB, 2B is not one. There we go. So there we have our question. What do you guys think? Is it true or is it false? Because the subset, proper subset of, is an operator. It requires a set on the left-hand side. It requires a set on the right-hand side, but it returns a value that is either true or false. So in this case, is it true or is it false?
False.
False. It is false. It is true. Okay, so every natural number, sorry?
Okay, cardinality. Cardinality equal.
Hmm?
I think he's okay.
Oh, it's perfect. Okay.
Cardinality.
Okay. So, sorry, go ahead.
Okay, I missed.
Okay. Okay, so let me just kind of answer this question first. It is true. Every natural number is an integer. Okay, well, that's great. So the next question is, if we compare the cardinality, it would make sense, right? It makes sense that the cardinality of the set of natural numbers would be less than the cardinality of the set of integers. But that is actually not true. So this is really kind of weird because both have an infinite number of elements, and yet one is a subset of the other one, but the cardinality is not one being less than the other one. They turn out to be the same. Okay? So now we want to investigate why they are the same. So the question is, can we make a bijective function? And I would use the notation that we have already introduced in this class. So f is the name of the function, and then now we need to name the domain and the codomain. So the domain in this case would be the set of all, well, let me see which way I want to go first. Let's go from natural numbers to the set of integers. So this is our objective. Can we make such a function? Yep.
Why do you need a bijective function to prove the cardinality?
I need a bijective function in order to establish that they have the same cardinality.
How is that? Why specifically a bijective?
Because with a bijective function, it's guaranteed to have an inverse. So if you can go in one direction, you can go the other way. So it kind of makes sense that if there exists a bijective function between a set A and a set B, then the two sets can be called to have the same number of elements. Because for every element on this side, it maps to at least exactly one element on the other side. But the same can be said when you reverse the direction. For every element in the codomain, it also maps to an element in the domain using the inverse function. Okay, so this is why it is important to understand what is bijective, because it means if you give me one thing on one side, I can tell you what it maps to on the other side, and it has to be unique. But on the other hand, if you grab me something on the other side, I can also tell you exactly what maps to it, and it has to be unique as well. All right. So we want to find a function that can serve this purpose. And of course, we already know that function. And for those of you who read the module ahead of time, it's going to go like, oh yeah, we kind of know that already. But I'm going to give you an example, first, like case by case, and then we'll try to figure out the actual expression to get it done. So what we want to do is to say, okay, let's map 0 first. I want to map f of 0 to 0 itself. I want to map 1 to 2. I want to map 2 to 4, and so on. So that means for all the non-negative, oh, this is going from, okay, that still works. Let me see, would that work? I think I reversed the direction, excuse me, so I'm gonna flip this. I think in my notes it is actually correct, but, in here, I'm going to flip the direction here. So this is one, for all the non-negative integers, they map to even natural numbers. And what about the negative numbers? Well, f of -1, I want to map it to 1. And then f of -2, oops, -2, I want to map that to +3. And then f of -3, oops, I want to map that to 5, and so on. In other words, if I see a non-negative integer, it maps to an even natural number. If I see a negative integer, I map it to an odd number, an odd natural number. So does everybody kind of see what is going on here? So if I keep going like this, don't you think this is, well, first of all, is it a function? Remind me again what makes a function a function. For every element in the domain, it has to map to one and only one element in the codomain. So we don't care about injection nor surjection at this point. I just want to make sure that this is a function. So the question is it possible for me to find an integer where it doesn't map to anything? No, this should cover it all, right? Because one covers all the non-negative integers, and the other ones covers all the negative integers. So that covers all the integers. Second question, is it possible for me to map one integer to 2 natural numbers? No, doesn't look that way. Okay. So the next question is, okay, it looks like this is going to work, but what about the closed form of this function f here? In other words, if I were to define f of x, equals to blah blah blah, that makes use of x, what would that be? What would these dots be if I want to define it as an expression? Now, some of you have already read the notes, so it is not too big of a mystery. We're going to use a ternary expression. That's one of the easiest things that I can do here, is if x is less than 0, I will use whatever is in this pair of parentheses. Otherwise, if x is greater than or equal to 0, I'll use whatever is in the second pair of parentheses. This is the ternary expression. I would hope that by the time you get to CISP440, that you would understand what a ternary operator is. If you want a quick reminder, I'm okay with that too. Does anyone want a quick reminder of what a ternary expression is? Okay, very good. All right, so I'm going to use the right-hand side. when you see a ternary expression, you can recognize it because it has a question mark and also a colon. So these two punctuations will separate the expression into three different parts, hence the name ternary, okay? Because ternary means three of something. The first part, which is a condition, you need to evaluate it first. If this is true, then whatever is in the middle, which is this portion here, becomes the value of the entire ternary expression. On the other hand, if the first part is false, then we use the last expression or the third expression, and the value of the third expression becomes the value of the entire ternary expression. Is that okay? Okay, all right. It's basically an if then else in a single expression, in a single thing.
Yeah, that's what I was realizing when you said it.
Yep. So different programming languages, have different ways to express this, but this is the syntax of C, C++, Java, JavaScript, just basically anything that is derived from C or C++. All right, so now that we have separated into two cases, x being less than 0, x being an integer but less than 0, versus it is not less than 0, let's see what should go into the middle pair of parentheses here. If it is less than 0, we want it to map to odd natural numbers. So that means we first have to negate x, okay? That seems to be something that we need to do because, in this case, x is going to be negative, and yet it is mapped to non-negative natural numbers. The second thing we need to do is to go like, well, we seem to be skipping stuff, right? Because -1 maps to 1, -2 maps to 3, -3 maps to 5. So we're skipping all the even numbers. So the question now is, well, if we need to skip, I think ×2 is going to do the trick. Okay, not quite, okay, but we'll get closer because, with ×2, we are skipping every other number. So now it becomes negative 2x. So if you use negative 2x, what happens when x equals to 1? Negative 2x is 2. What if x is negative 2? Negative 2x is 4. What if x is 3? Negative 2x is going to be 6. We're still off by 1. But off by 1 is easy to fix by either subtracting or adding 1. But in this case, are we adding or subtracting? We're subtracting because negative 2x is just 1 too big for what we want. So we just need a subtraction of 1. And there we go. So that takes care of mapping the negative integers to odd natural numbers. Yes?
Do all two sets of the same size have a bijective function that can map to both sets?
You can make one.
Okay.
So the best I can say is if you have two sets and they have the quote unquote the same number of elements, then a bijective function exists. Now, how you want to define that bijective function or which bijective function you want to choose is up to you. But I would say at least one exists. Sure. So this is by no means the only way to do it. This is just one way to do it. All right, so getting to the last pair of parentheses, which is this pair here, which takes care of business when x is not less than 0. That one is easy to do, isn't it? Because 0 maps to 0, 1 maps to 2, 2 maps to 4. Looks like it's just 2x to me. So we'll go ahead and say this is exactly just 2x. And here we have a function. So this function, in this particular form, is generalized. I'm not giving you the two tuples. It is just defining, how we are going to map integers to natural numbers. Are we good so far? I'm not going to go into the details, but I will give you the framework of showing that this f is bijective, which means we have to first show that it is injective, and then we have to show that it is surjective. I said, it's not going to be formal because I don't want to formally introduce proof by contradiction, but it is an essential and important proof technique here. So proof by contradiction basically says, let's assume it is not and see what kind of trouble we can get ourselves into. That's basically the basic idea of proof by contradiction. So in this case, if we claim that this particular f is not injective, that means if you give me, it's possible to map two integers to the same natural number. That's basically what it's saying if we say that f is not injective. And then what we need to do is to say, okay, let's just say that is true. Let's say this f here is not injective. Show me why it is not possible to map two different integers to the same natural number. So you basically have to start with f of, you have to start with two different values. So we'll call those y and z. And we basically say f of y is going to be the same as f of z, even though y and z are not the same. And then we have to do the proof using algebra to show why that is not possible. That's proof by contradiction. And we can also use proof by contradiction to do the other way to show that this has to be surjective as well. Can someone remind me again, what does that mean? If I say f is surjective in this particular context, what does that mean? Yep.
Surjective means that every element of the codomain is mapped to some element in the domain.
Yes, so every element in the codomain is mapped from one, let's see, is mapped to. Now, it is possible to have multiple elements in the domain to map to the one single element in the codomain. It will still be surjective as long as every element in the codomain are mapped to. Okay? So to show that this is surjective using proof by contradiction, we basically say, let's say it is not. Okay? Let's say this f is not surjective. Then we have to show that it is not possible to have a natural number not mapped to. We assume that there's one, and then we say, okay, let's say this is not mapped to, but I'll give you a way to find out who really is supposed to map to this element in the codomain. So if I can make that argument, that basically says, oh, okay, so it cannot be not injective, it cannot be not surjective, it must be both, and hence it has to be bijective. Now, since we already know, f of x, we can actually do something like this. Okay, this is going to be much more conclusive, which is to figure out what is the inverse function of x here. So this means if you give me a natural number, I can tell you exactly which integer maps to this specific natural number. Are we good so far? All right. So the question now is, what are we going to do? I mean, how do we get started with something like this? Well, it looks like the main differentiation is whether it is even or odd. Okay, whether the given natural number is even or odd. If it is even, we treat it in a particular way to find out what integer maps to this natural number. If it is even, then we do something else. So it would seem to make sense that we are going to use a ternary expression here as well. Except this time, the condition is to see if something is odd or even. So to check something is odd or even, how would you do that? What is mod? Okay, very good. So we'll say x, what do we mod it with? 2, very good. Okay, so x mod 2 is the remainder of x divided by 2, which can be a 0 or 1, and what do we want to compare the remainder to? You can compare to either one. So let's compare to 0, okay? Now you can compare to 0 using equal to. You can also compare to 0 using not equal to. It just kind of flips the second and the third part because it just flips what is true in one case becomes false in the second case and so on. So it doesn't really matter which one you want to choose. It's just a matter of what makes it more natural. So I think most people want to compare to 0 to look for equality instead of look for inequality. So we'll just go for equality here. Now, if that is the case, what is corresponding to the middle pair of parentheses here? It's going to correspond to when x is even or odd. It's even, very good. So if x as a natural number is even, what do we want to do with it to reverse the operation of f? So let's take a look. So when we look at f itself, if the doubling of x, which results in a even number, is when x is greater than or equal to 0. So that means, starting with x as a natural number, which is by itself greater than or equal to 0, we also want to end up with a value that is greater than or equal to 0. So that means we cannot be negating it. But since it is doubled because of the 2x here, what do we do to reverse the doubling? Divided by 2. Okay, very good. So we'll go ahead and divide x by 2 in this case to reverse it. And that will take care of the case when the natural number is even. It will map it back to the non-negative integer, in the opposite direction. So now we look at the third pair of parentheses over here, which is corresponding to x mod 2 does not equal to 0. In this case, that means x is odd. So how did we end up with an odd number? Well, the only way we ended up with an odd number is over here. So we want to be able to reverse negative 2x minus 1. So as a I shouldn't say natural, but as a way to reverse a compound operation, what do? Because if you look at doubling, we know how to reverse doubling, right? Or reverse multiplication by a constant. We just divide it by the constant. We also know how to reverse subtraction by 1. We just have to add 1 to it. The question is, what is the order? So to illustrate that, I am going to show you the order of operation. Well, there are several ways to do that. I can show you the order of operation just by adding additional parentheses, like so. So this shows me that we are first multiplying x by negative 2, then subtract 1 from the product. So when you're working with inversing a function, what do? What is the order of applying the inverse? In this case, we know the inverse function involves adding 1. It also involves the division of negative 2. But in what order?
You add and divide. You add it first and divide.
You add first and then you divide because the operation has to be opposite. Let me get some water first. So you're correct. We're going to add 1 first, and then we divide it by negative 2. So over here, we have a division by negative 2. But before we perform that, we have to add 1 to x first. All right. So the inverse function of f in this case is also bijective. It has to be. Because in order for f to have an inverse, f being bijective is a requirement. But if f is bijective, f inversed is also automatically bijective. So now we have a two-way street. You can give me a natural number, any natural number. I'll tell you which integer maps to that natural number. Or you can give me an integer, and I can tell you which natural number it is supposed to map to. All right? But this is crucial because now that we know f is bijective, now we can say the cardinality of the set of integers is the same as the cardinality of the set of natural numbers. The cardinalities are the same between those two sets. despite one being a proper subset of the other one, which is counterintuitive. It's like, how can that be the case? Because there are things in here that cannot be found in the other one, and yet they have the same number of elements. Because we establish equivalence of the cardinality, not by counting, because they're both infinite, but by establishing there is a bijective function between those two sets. Yes?
Do all functions that have an inverse imply that it must be a bijective function in the first place?
Yes. Yep. Only bijective functions have inverses. So every bijective function has a inverse function. Very good. So good observation. Yep, go ahead.
I'm not understanding how the cardinality is equal universally when we had to filter it through a function first.
That is basically how we define it. So this is basically how we define the equivalency of the cardinality between two sets, each having an infinite number of elements. In this very specific case, we can even claim a little bit more. It is probably in the notes already, but I'm going to type it up here. Okay, so given a set, we'll call this X. Okay, if there is a bijective function, and this time I'm not going to use G because we use G for something else later on in today's class. I'm going to use H here. So if I can define a bijective function H from X to the set of all natural numbers, then the cardinality of X is the same as the cardinality of the set of natural numbers, which is known by this definition to be Aleph null. Aleph null. There we go. That is a definition. So for those of you who are curious, because someone is going to be saying, so if this is Aleph null with a 0, this has to be a Aleph 1, Aleph 2, Aleph 3, and so on. And there are. But in this class, we are only concerned about Aleph null, which by definition is the cardinality of the set of natural numbers, which turns out to be the same as the set of integers. Is that okay so far? Okay, great. So at this point, we're going to shift our attention to filling up tiles in a two-dimensional space. This is going to be fun. So to do this, I need to run a script first. So give me a little moment here to run that script. Because otherwise, the coordinate of my stylus corresponding to screen position is going to be off. So I need to run this script to fix that little problem first. And now we can do this. We can look, you guys can look at the mirror of my tablet screen while I switch back to the actual tablet screen to actually draw something. All right, so what we are concerned now is to consider a two-dimensional space. And for the discussion, you can basically just look at this as a screen, and we are just looking at pixels on the screen. So I'm going to go ahead and just draw the corner of the space, and we'll call this particular pixel here, we'll call this 0, 0. And then we'll call this row 0. Oh, okay, I just made a mistake here. This is 1, 0, because the x coordinate is 1, the y coordinate, which is corresponding to the row number, is 0. And this one here, we'll say this is 0, 1. And obviously, this is going to be 2, 0. This one here is going to be 1, 1. And then this one over here is going to be 0, 2, and so on. So first of all, do we have any questions about how I use a two-dimensional coordinate to name each pixel of this space. It's a two-dimensional space, and then each pixel has a coordinate. The first one is quote unquote the x, which is which column it's belonging to, and then the second one is the y coordinate,